Alright.
Bahasan kita hari ini, kita akan mendengarkan pemaparan Dr. Nadiah mengenai high pressure processing, kemudian pulse electric field, dan juga ultrasound processing. Jadi teman-teman mahasiswa mohon mengikuti dengan baik. Nanti akan ada sesi diskusi ya setelah pemaparan dengan Dr. Nadiah. Mohon aktif untuk bertanya atau memberikan ini ya sharing pengalaman gitu ya mahasiswa apa yang dihadapi ketika Anda melakukan teknik pemeriksaan tersebut. So actually Dr. Nadiah, students have already performed practical skill about ultrasound.
Okay.
If I'm not mistaken, they already extract bunga telang.
Bunga telang.
Maybe YT, maybe I will ask again. So for
Okay.
So the student will discuss more with you for ultrasonic extraction actually after the presentation. So without any further ado, Dr. Nadiah, time is yours.
Thank you so much, Dr. Asri. Yes, as she has mentioned, please, I welcome any sort of question that you have in regards to your experimental work. Maybe if you want to ask opinions, or maybe you would like to show some of your results just for discussion's sake, no problem. And you may pose your question in bahasa atau in English. I understand Indonesian language if it's used in standard ways, but I cannot speak it. That's the only problem. Okay. All right. So let us continue with our lecture for today. Okay. So for this week, we are going to be discussing on the high pressure processing, pulse electric field, and also ultrasound processing. Okay. So I'm just going to go a bit of basics of those technologies today. Okay, so applications of non-thermal basically has been deemed as an alternative treatment for food processing, which are gentler in comparison to conventional thermal method, because we want to, to avoid the degradation of the qualitative characteristics of your food. Okay, so many researchers have done on the non-thermal technology of food processing and has reported on the minimal or no effect of non-thermal technologies towards any food attributes, either in the nutritional content or the quality, or maybe on the, and maybe perhaps sometimes non-thermal can also, improve the quality of your food. However, due to the uniqueness of food type, because of the food matrix, the composition of the food itself, certain methods can only be done on a certain product. Okay, so when we are discussing on the pulse electric field, back when I was studying, I think about 10 years ago, pulse electric field was only done on liquid food, but now they have done it on solid food too. So we look at the technologies, and we look at the appropriateness of using that technology onto the food product. Okay, so with that, only a certain non-thermal technology can be applied to food with the aim to inactivate pertinent microorganisms. This is the main objective, obviously. Sometimes we want to also inactivate naturally occurring enzyme, but at an optimized process, so that minimal effects towards the quality of the food with minimal cost, and of course the energy usage, because we are moving towards the sustainable development goals. So we like to use lesser energy, lesser water consumption, and of course we want to improve the production of our food processing. Okay, so when we look at the food preservation, we have this. Okay, so I have divided into two sections, which is the novel thermal and the non-thermal. So if you look at the non-thermal, when you list them down, you could see the source of the non-thermal treatment. Okay, so for instance, high pressure, of course, we're talking about pressure. Talking about pulse electric field is basically an electromagnetic. So it is more or less the same as the infrared heating and of course the microwave heating. But we will discuss about that later. And when we're talking about ultrasound, we are discussing the source of the treatment comes from the sound wave. Okay. So the key drivers, obviously, we want to kill off the microorganism. We would like to produce safe food with minimal effect to it. So basically, the consumer wants freshness, convenience, and less preserve. Okay, so because of that, we would like to also enhance the safety and extended shelf life because as you can see, production nowadays, especially in Malaysia, even in Malaysia, we would like that our product that is marketed on the shelf to be more than 1 year minimum of shelf life. Okay, because we would because with that we could lessen the wastage. Okay, and of course we would help the economy better, the production of the food. So there's a lot to it. Okay, not just to extend the shelf life for your own consumption, but also for the producer and of course for the farmers. Okay, so any heat label meaning any heat sensitive ingredients are retained, such as vitamin C, any other bioactive compounds. And of course, when we're talking about sustainable development goals, we are going to have lower carbon footprints and reduce water consumption in heat transfer processes. And of course, we are using the engineering functional ingredients. Okay, so sorry, we're not using, we are producing what we are engineering functional ingredients for delivery of healthy food. Right, so advantages of it, basically, we are just looking on the overall part of it, which is sometimes we can enhance the extraction of sugar and cellular content. I guess I'm sure you guys have done on the ultrasonic part, where you can extract the anthocyanins color of bunga telang and by using a minimal processing. And of course, I think if you would like to test on the microbial part of it, and then basically you would see that there's no microbe, within your food. It also sometimes can help in drying plant tissues. And of course, you can inactivate or maybe even modify enzyme activity. And at times, it can be used as a hurdle method so that you can use mild heating with your non-thermal technology, right? So the current processing trend, if you look at this, there's a lot of newer technologies that are coming in, okay? So these are the traditional food processing where we use formulation, blending, fermentation, MAP, sous vide, and biopreservation. But the novel technology now are basically on the molecular gastronomy. We are also looking into 3D food printing, microencapsulation, okay, edible films and coating, vacuum impregnation. Vacuum impregnation is used to retain the moisture inside your vegetables and fruits so that it can be it can last longer. Right, so there's a water in oil, in water emulsion. We usually see water in oil or oil in water, but now water in oil and in water emulsion. So when you look at the non-thermal extraction, these are some of the extractions. So besides ultrasonic, you can also use homemade drying, colloid gas aphrons. There's also the pressurized microwave assisted pulse electric field. So there's a lot of things that you can use and compare with your ultrasonic method of extraction. And when you look at the non-thermal processing, basically, or what we call non-thermal preservation, you can also use some of this, right? So when we look at the current, the global non-thermal pasteurization market trends, if you look at this, of course, the bulk of the technology will be in North America because most of the technologies are being, developed there by their universities and then adapted by their industry. Okay, because they are also the major food producer of the world. And besides that, we also have the European countries, and Asia Pacific is quite small in that sense, but it is there. So the trend is expected to be worth about 6 billion by 2028, so growing at about 20%. Okay, so the attractive opportunities is because we are witnessing gradual growth due to the rising usage of novel technologies to extend shelf life. So we here in Malaysia, we are looking into producing product with a shelf life of about 1 to 2 years. But in the United States, they are looking to produce a food product that can withstand up to 6 years or more. Okay, because we are looking into global populations that's going to be growing at about 10 billion in 2050, sorry. So the issue is that the food production cannot cope with the demand of the population. So basically, what the United States are doing now, they are producing ready-to-eat food that can be kept at ambient temperature, basically at room temperature, and can be kept at a longer period of time, 6 years or more. Because we are also looking at not just on the global population that is increasing, but we're also looking at the natural disasters that are increasing. We are looking at the production of our raw materials going to decrease because of the war that is incoming, and of course the war in Russia and Ukraine. So there's a lot of things that we need to look for. So that is why if you look at this issue or this technology, in general, North America is very, very aggressive towards it because they would like to maintain the type of food that they have now and at least to cope with the population of North America. Okay, so if you look at the food manufacturers are also looking to boost processed food production levels to address the changing demands of the consumer, to expand, okay? So when they expand, of course, you would have more money and of course the geographic footprints, and of course, you are also looking at the Asia Pacific market growth that is increasing because of the investment by the manufacturers and of course consumer interest towards processed and ready-to-eat food product. Okay, you look at the non-thermal pressurization companies. Okay, so this one is actually I think it was a Swedish company. JBT is actually under Japan. Hyperbaric is if I'm not mistaken, it was a Spain company. Okay, Cobelco is Japan, Multivac is a Germany company, Stansted is actually in Netherlands. The Netherlands, the Dutch company, Pulse Master is actually Pulse Electric Field that comes in from United States. So these are the main producer of non-thermal technologies. Okay, the issue with non-thermal technology is that it's not as simple as you try to cook your food product on top of the gas stove and then making sure that there's no any microorganism that survive. And of course, sometimes you don't want any enzyme issues. But with the thing with non-thermal is that there's a lot of trial and error that comes with it. Okay, so it's not a straight process. It's not from A to B. So it's basically from A going to B is like the process design, the hazard analysis, the validation of your result, and of course you have to go for the regulatory acceptance. Okay, because if you're looking at the food regulation, especially even in Malaysia, we use US FDA, United States Food, Drug and Administration standards as a benchmark. So often when they revise their benchmark or their regulation, Malaysia under the Ministry of Health, under the Department of Food Safety and Quality Division would also change our food regulation. So if you look at, this is how they come up with the TRL, the technology readiness level. So every new technology has to go through these steps. So they have to make sure that the basic principles are observed and reported until to the point where it is ready for full-scale commercialization. Okay. Because of that, at times, novel processes or what called the non-thermal technology takes a lot longer to be approved by the US FDA. So you could see here, it was only in 2001 that UVC was accepted in part of the food regulation to be defined as food additives. It's not even as a food preservation, but as a food additive. Okay. In 2004, USFDA approved HPP as an intervention method. It's not even a preservation method. Okay, for listeria contaminated RTE wheat product. In 2008, they approved irradiation of fresh iceberg lettuce. If you could see, okay, every regulation here is very specific towards what? Okay, so towards listeria contaminated RTE, towards fresh iceberg lettuce, so is very, very specific, and it would take longer period of time for them to be approved, only then for the industry be able to adapt or to adopt the technology and to use it for a commercial scale. Okay, so we go to our first subtopic of the day, which is the high pressure processing. So what is HPP? So HPP is basically a technology that uses pressure of about more than 100 megapascal, but it needs to have a liquid or water as a medium transmitter. Okay, so it was first researched by Hyde et al. There was a Japanese guy to pasteurize milk, and it was then commercialized again in Japan in 1990. Okay, to treat acid food and for chill storage. Okay, in 1991, yogurt, fruit jellies, salad dressing, and fruit sauces were also introduced, and two Japanese fruit juice processors installed a semi-continuous high-pressure equipment for citrus juice bulk processing. Okay, if you could go back to what I have said, okay, so this Japanese guy first researched in 1899. It was first commercialized in 1990 in Japan, but it took about 14 years for the US FDA to approve the usage of high pressure processing in United States. Okay, so the high pressure treated food has since been marketed in Japan since 1990, in Europe and US since 1996, and of course in Australia in 2001. So this is the general schematic diagram of a HPP. So what does it look like? Basically, you need to have a vessel. It's a very good vessel. Okay, so you need to fill in your food product, and you also need to fill in with water. Okay, so then you will turn on your pressure transmitting medium, then it will gives out a very high pressure impact to your food product. Okay, so basically, if you were to compare HPPs, it looks something like this. If you were to have a 10 cent in your hand now, imagine it is being stepped on by two adult elephants. So that is how much of a pressure that was being put onto your food product. The best part about HPP is that your food product is actually it can be independent of any product size, any geometry. So the effect of the HPP is uniform and of course instantaneous. Okay, the word that we would use is isostatic, meaning uniform pressure. So imagine this is your food product. So the pressure will come in from all directions. Okay, making sure that you would have isostatic pressure. So the process temperature can be specified below 0 degrees C to 100 degrees C. Okay, and exposure time is just between milliseconds to about 20 minutes. Okay, if you look again, like how much of a pressure, like sometimes even I myself cannot even imagine, like, how much is 100 megapascal pressure. Okay, if you look at the sea level, okay, probably we are living at about sea level or even a bit higher up. The pressure is about only 101 kilopascal, and it is only a kilopascal. So if you were to go down deep into the ocean, okay, so the HPP that we have in UPM produces at about 400 to 600 megapascal. Sorry. So it's about 400 to 600 megapascal. So how deep of an ocean we need to go through to reach to this level? It's about here. Okay, it's about 400 to 600 megapascal. So we are talking about here at the 4,000 to 6,000 meter of seawater, where basically you are looking at a frightening looking creatures, you know, fishes with fang tooth, with flashlights, the types of fish that we do not see. Okay, and then of course we are talking about the Hadal zone. Okay, that is how big of a pressure that we are using to treat our food product. So usually we use about 200 to 800, 800 being the highest pressure, but the hyperbaric HPP that we have in UPM, it is at about maximum of about 600 megapascal, right? And it is the optimum pressure for processing commercial food products. So principle of HPP is based on two, right? So there's what we call the Le Chatelier principle, and of course the isostatic principle. So Le Chatelier stated that, okay, any phenomenon, any phase changes, meaning from liquid to solid or from gas to liquid, is accompanied by a decrease in volume, is enhanced by pressure. So what you are looking at is that your product will shrink. So that is why we need to use liquid as a medium. Okay, we will discuss more after this. Right, so another principle that we are using is the isostatic principle, basically a uniform pressure from every direction and then return to their original shape when the pressure is released. So the product are then compressed, okay, independently of the product size and of course the geometry, because the transmission of pressure to the core is not mass or time dependent. So the process is minimized, right? And if the food product contains sufficient moisture, pressure will not damage the food product at the macroscopic level, as long as the pressure is applied uniformly in all directions. Okay, with that, I would like to mention that for this, for HPP is usually recommended to use for products that has water content in it. Okay, for products such as bread that has very minimal water content, for biscuits or crackers that has very minimal water content. Not that we do not, of course, we do not need to treat them, because with minimal water content, you basically don't have any microbes available, right? But again, with the limited water content it has, when you put inside the vessel of HPP and then you pressurize it from every direction, basically your biscuits that come out will not look like biscuit anymore. It will look like dust. Okay, so that is why we need a food that with sufficient moisture. So the process description looks something like this. Okay, so you would have a basket. You put your product into this basket, and then you put your basket inside the vessel, and then the water is pumped into the HPP chamber, and then they make sure that the vessel is tightly closed from every direction. There's no leakage of holes, and then it will be pressurized. Okay, then the product will be held at an isostatic pressure, okay, to inactivate microbial activity. How long? It depends on your product. How many of it? What is the thickness? Okay, if it's very thin, then you don't need a long time to pressurize your product. Okay, so HPP product will come out at the end. Okay, once it has decompressed, basically you have released all the pressure from the vessel, and then it has released all the moisture, all the water that is within the vessel, and then you can have your product. So the key benefits are basically you can reduce the pathogens, okay, no microorganism. Sometimes the shelf life can be extended to 10 times, okay, longer. It enables clean labels, so you don't need to use any preservative. So any chemicals is not needed. It reduces food waste, because the food product that you are producing, you know, are able to be kept a longer period of time with very minimal quality degradation. And with that, you can maintain the taste, the texture, and of course, the nutritional value. And obviously, you can protect your brand reputation. Okay. So types of HPP, there's two. One is what we call the direct compression. Okay. So you put your food product here. Okay. So then this piston will pressurize, it will move downwards to pressurize this vessel. So this is what we call the direct compression. Another one is what we call an indirect compression. So the ones that we have in the market now, the commercialized HPP is basically an indirect compression, where you have a vessel, you put inside your food product, then you have the medium fill in the vessel, and then the pressure will come in from the outside. Okay. So these are some of the commercialized HPP. Okay, we have this in Malaysia. It's very nearby UPM, my university. But the only downside of this technology is that it has very small basket here. I can only put maybe 2 packets of my product. The maximum level is about 1.5 liter, that's all. This one is stated here 2 liter, but usually the 0.5 liter we need to put in the liquid medium. Okay, so this is what it looks like. There's a new one that we have acquired. It costs about 8 million ringgit Malaysia. Okay, so this is what it looks like. So basically you can put a lot more of your product. So you can see the basket are quite big, quite large. You can put in all your food product. So it is using a horizontal design for easy installation, easy usage, and of course there's traceability. And it is a special design for food industry, uses stainless steel, cleanable, okay, easy to clean. It has an automatic loading and unloading system, and the working pressure is up to 600 megapascal. If you look at the evolution of HPP, so it started off in 1998. This company here, Hyperbaric from Spain. So it started off in 1998. So this is what their initial HPP equipment looks like. It needs to be buried underground because they was too scared that it's going to burst or it's going to explode. All right. So then they came up with a newer technology where it has a bigger vessel. Okay. I'm not talking about the vessel inside. Yeah, I'm also talking about the outer vessel that protects the people, the workers, the equipment. Okay. So they have even bigger, and now they have produced what we call a 500 liter bulk. So instead of just putting all your food product in a packaging inside this basket here, now they have basically something like this. So you would have a flexible bag. Okay, this one can be taken out, can be clean and everything. And then they just pump your fruit juice inside this flexible bag. So you no longer need any liquid transmitter. You no longer need to put in any water. So then they just they just pressurize it. Okay, so it looks something like this. So you're filling the juice into this flexible bag and then pressurizing for a few minutes, inactivation, and then unloading, and then the HPP juice sent to filling and bottling line. Okay, the best part of using HPP is that your food product often do not increase in temperature. So it does not, your fruit juice is not hot when it come out, so you don't need to use any cooling equipment. So, and then it's quite convenient to use. Okay, so this is a multi-vac coming in from Germany. So this is what it looks like. It's very, German specification. Okay, so the processing operation. The basis of applying high pressure to food is to compress the water surrounding the food, the liquid transmitter. Okay, so at room temperature, the volume of water decreases with increase of pressure. Okay, because liquid compression results in small volume change, high pressure vessel using water do not present the same operating hazard as vessel using compressed gas. So that's why it's quite safe in comparison to using compressed gases. So the volume decrease as the pressure volume decrease as the pressure increase. Okay, another thing that you need to be mindful of when you are using HPP to treat your food product is the number of cycle. Okay, so this is the number of cycle, basically the come up time, the time that you need to wait for your pressure to build up. Then there's what we call the holding time. The holding time is the time where your food is actually being pressurized. Okay, and then you have to wait for the decompression time. So this is the come up, the holding, and the decompression time is what we call what we call as one cycle. Okay, and then the volume of the product, okay, and then the number of high pressure vessel available. Okay, because of the newer technologies, the advancement of it, so now it's taking less and less time to pressurize your product. So the productivity is basically has increased. Okay, so the pressuring time is reduced by increasing the delivery rate. Okay, when the required operating pressure is attained, the pumping rate is reduced. So if you are able to have a come up time that is very, very fast, if you are able to close this gap, minimize this gap, then you can also increase your productivity. Okay, the same goes with the decompression time, because at the moment, these two timing is what we call the unproductive time, because it is not doing anything to the product. Because we are considering holding time or holding pressure as the treatment time, okay, as the treatment process. Okay, so if you were to use basket, and if your product is basically, being put into a packaging, okay, we would like for you to basically, achieve at least 75% of loading. So because this one is what we call a poor design, because you basically have, you have gaps here and there. When you have a lot of gaps, then that means you need to use a lot of water, right? So the best design, if you can put in all your food product into one vessel. Okay, so that's why we recommend that for HPP, we use a flexible packaging, okay, that has more than 50% volume contraction. It is able to withstand any decompression or the volume decrease during the pressurized treatment. So it has an extra tight seal so that the water that is within the vessel do not goes into your food product. It needs to have a minimal headspace, meaning to say that your food product is being filled to the top. Okay, so it doesn't have a lot of space. Okay, and of course you need to have a test strength. Is not easy to tear, atau what do you call it, koyak, right? And okay, so that is what we require of HPP packaging. But kalau if you are using the bulk processing, then you don't need to worry about the packaging. You can use any type of packaging that you would like to use. Okay, so processing operation. So this is the optimum pressure, 400 to 600. If you were to use at about 300 pressure, you are able to deshell. Okay, deshell your lobster, deshell any shellfish. So you can easily shuck them out, meaning shucking, keluarkan isi shellfish tu, okay, daripada cengkerangnya, right? So if you were to use this at about 400 to 600, these are all the product that you can use. So you can use it on fruit juice. This is what we call guacamole, from avocado. What else? This is, I think, ready to eat salami, meat product. Okay, so if you were to compare, these are basically the fresh ones. Okay, control. This is the color is quite fresh. Okay, if you were to use 200 until 600 megapascal, obviously there's going to be some changes to it. So that is why we minimize the usage of HPP to up to about 300 megapascal. Where it is still edible, the texture is quite nice still. Okay, and if you were to combine freezing your meat with high pressure processing, then it's even better. If you look at the 300 megapascal, it looks a bit more better than the fresh ones. At 200 is even better. Okay, so if you look at the effect of HPP on the biological materials, when we're looking at the microorganism, which is the main goals of us doing non-thermal treatment, is basically to kill off the microorganism inside your food product. So the microorganism has been categorized into two categories. Okay, one is what we call the gram-positive. Okay, one is what we call the gram-negative. So the gram-positive basically has a very thick peptidoglycan layer absorbing the surrounding materials or even your toxin. But it is easier to kill. for gram-positive, it's much easier to kill, and it develops resistance lower. But we are talking about gram-negative, although it has a very thin peptidoglycan layer, but it has a multiple layer that your any treatment has to go through, right? So that is why the issue with the gram-negative is most often it can develop resistance towards your treatment. Okay, it's harder to kill. So what happened, let's say if you were dealing with a gram-negative, is that at times it can revive or resuscitate. So even after HPP, it is what we call just only having apa orang kata, they call it a cedera like that. Okay, so a bit rosak here and there, but it can revive when it has a good nutrient. Sometimes it only needs sugar, okay, for its food, then it can revive and then hidup semula di dalam makanan. Jadi that's not what we want. We want a kill off, okay? We want to kill off everything. So when we are dealing with gram-positive, then it's easier, okay? Most often we are just killing them directly, no revival, no resuscitation, and then you are producing safe HPP food. But then again, we need to know the type and number of microorganisms. If it's a lot, then maybe you need to increase the treatment time or maybe the treatment pressure, okay? And the magnitude and duration of the high pressure treatment, temperature, and of course the composition of the food itself. So if your food product has a very high sugar content, most often the bacteria can regrow, or what we call the revival, right? So the main important thing is to sometimes to combine the HPP and of course temperature, okay? But the maximal temperature at about 15 to 30 degrees C is not effective in killing all the microorganisms. We are looking into freezing temperature or sub-zero temperatures, okay? Or even elevated 40 degree or more for the efficiency of killing all those microorganisms. And of course, when we're looking at the food matrix, like I've mentioned, so sometimes food constituents or the soluble solid inside your food product may able to protect microorganisms from the effects of the high pressure. And at times when it has, cedera, and sometimes the sugar, the free amino acids, and even vitamins are available, and therefore the cells are protected, or it can even revive or regrow. Okay, these are basically microorganism and inactivation kinetics. It really depends on the type of microorganism again. So that is why I've mentioned that for HPP or any non-thermal treatment, we need a lot of trial and error to do, because we would like to make sure that everything is being killed off efficiently. Enzyme is actually influenced by pH, the substrate concentration, and of course the subunit structure of the enzyme, and temperature during pressurization. So if you look at this relative activity of enzyme of ALP or alkaline phosphatase in raw milk after 20 minutes of pressure treatment. So at a higher pressure, the relative activity goes lower. Okay, so these are actually the enzymes that we would not like to have in our milk product. So factors to consider, especially when to implement HPP, is of course, the cost of it, right? The cost will highly depends on the processing condition, the pressure, time, temperature, the cycle time, capital cost, depreciation period, the maintenance part of it, the labor cost, the energy, water cost, okay, exchange rate. So most often obstacles in implementing HPP is the low level of public knowledge, okay? As I've discussed with Dr. Asri last week, most often we do not have the experts in our country, okay? And the lack of explicit support for wider use of technology. HPP is very, very expensive, so SME often, or small medium enterprise often cannot afford to use it. Okay, and it also has an image of high cost, has an image of high technological sophistication, reduced number of suppliers. If you look at HPP equipment producers on the Multivac, JBT, Cobelco, there's not a lot, and because the currency exchange, sometimes this may hinder your wanting of using this technology in your industry. And of course, you're talking about economical risks, you're talking about the mechanical, structural reliability, you're worried about the high investment costs, and of course, you are also worried about the approved protocol, because oftentimes, there's not a lot of research that has been done onto your product, because the one that has been researched at the moment is most often, steak, fish, and let's say I'm talking about, in Indonesian cuisine, or we do not have any research that has been done on sambal ayam penyet, something like that. So even in Malaysia, we do not have any research that has been done on nasi lemak. So we have yet to know what's the effect of HPP on nasi lemak itself. Okay. And for bulk processing, the high pressure equipment should be part of the aseptic line. Okay, so it needs to be clean and sterile. And of course, you need to have the pressure vessel that has a very short cycle time, easy to clean, be safe to operate with accurate process control. So this is one of the obstacles of implementing HPP. Okay, right. So we have gone through the first subtopic. So this is the second subtopic, which is the pulse electric field. So what is pulse electric field? So these are pulse master. These are the one that we have in Malaysia, okay, nearby UPM. But we do not treat solid food yet. We only have the equipment to treat liquid food. These are the newer technology that has been done in Netherlands. So they are basically now treating tomatoes and also treating potato in their industry. Okay. Now in Malaysia, we only have for liquid at the moment. So what is pulse electric field? So it is an innovative mild food preservation techniques. It applies electrical voltage or electric pulses to destroy harmful bacteria in food, and of course with the idea of prolonging shelf life without any quality loss. So usually it involves the application of high voltage. It is about 20 to 80 kilovolt per centimeter. It is being used to food that is placed between two electrodes. So I've mentioned about electrodes last week, right? On radio frequency and RF heating, and of course the infrared heating, right? But those two basically produces a wave that kill off the microorganism. But this one, it uses a literal voltage, a literal electricity in between those two electrodes. So this one is quite, I think, much more riskier to use in real life in comparison to the radio frequency or the infrared ones. Okay, so the process is based on pulse electrical currents that is delivered to the product placed between a set of electrodes. The distance between the electrode is termed as the treatment gap. Okay, what it needs to do is basically it needs to produce an electromagnetic field that exceed a critical transmembrane potential of more than 1 volt. Okay, what is transmembrane potential? Is basically your food cell. It usually has a wall. Those walls are what we call the transmembrane. So in order for your food product or for the pulse electric field to generate electricity, for it to kill off the microorganism, the electricity needs to be higher than the transmembrane potential. And it is often much more higher than 1 volt. Okay, so then from there, it results in a rapid dielectrical breakdown, conformational changes of the cell membranes, which leads to release of intercellular liquid and the cell death. Okay, so PEF treatment show changes in tissue structure, leading to weight increase and greater water holding capacity and less loss during cooking. And of course, the main parameters are the electrical field strength, pulse geometry and duration, and soluble solid of the treated food. Okay, so the engineering aspect of it. So basically, this is just the general overview of it. So it's very simple. Okay, so you basically have a treatment chamber, you have a wave controller. Oftentimes you have a capacitor to store your energy, right? So, and then it's being connected to what we call the HVAC. High voltage alternating current or high voltage direct current, right? And this is what in general it looks like. So basically you have a raw product material is being popped into a heat exchanger, and then from there it will goes to a pulse electric field treatment chamber. Then it goes through a cooling heat exchanger. Okay, why do we need two heat exchanger? One is to actually increase the temperature into what we call the mild temperature range. It's about 40 degrees C, right? And the cooling is basically to cool down. So sometimes this pulse electric field can increase the temperature up to maybe 60 degrees C, and then we need to lower it down to maybe about 20 degrees C, right? So that's why you need a cooling heat exchanger. Often, pulse electric field cannot pasteurize or cannot sterilize your food product totally. So that is why you need mild temperature. So pulse electric field are often used with mild heat treatment. Okay. And this is what we call the hurdle technology. All right. The combination of technology of any two technology. Right. Okay. The mechanism of it. So how does it kill off any microorganism, or at times how do you use pulse electric field to extract bioactive compound? I'm at the moment doing a research where I use a waste from banana peel to extract fructooligosaccharides. Fructooligosaccharides. So using pulse electric field, or we call FOS, from banana peel. Okay. Using pulse electric field. I have yet to see the result. My students are going to present it to me, so hopefully it's a good result. All right. So biological membranes, we're not just talking about the microorganism, we're also talking about your cell plant, okay, are considered as capacitor because it sometimes, you know, can have a flow of electrical discharge. So dielectric magnetic material of low permittivity, and they maintain an electrochemical gradient at both membrane sides. And this gradient can occur because of the excess of negative ions that are accumulated on the inside of your surface of the membrane, and to an equal number of positive ions accumulated on the outside. Okay, I've mentioned before transmembrane, right? So if your transmembrane, if the voltage of your pulse electric field exceed the transmembrane dielectric property or dielectric value, okay, so if it's much more higher, most often it will produce an irreversible damage to your cell. So then basically you can pasteurize your food product, and you know, you can increase the yield of your juice, you can extract biocompound, you can use it for freezing, you know, to help with the crystallization of your food. You can also dry your food product better, curing osmotic dehydration, and of course smoking. But if it's less than the if the dielectric value of your transmembrane is much lesser than the electrical value, is much higher than the electrical value of the pulse electric field that is being transmitted, so basically you would have an intact cell. Okay, and if it's not enough, then basically you would have a cell that is damaged, but then it can be reversible. So it can, you know, go back to its original size, then it can revive, regrowth, and something like that. So what happened is that, so consider this your two electrodes, okay? So this is your cell, okay? It could be your microorganism cell, it could be your plant cell. So what happened is that, so your voltage will come out, okay? And then it will be produced from the positive electrodes to the negative electrodes. So it will go through across your food product. What happened is what we call a polarization. So there will be a lot of electrical charges that will go through this your cell plant, and it will rearrange all the ions inside your cell plant. So if it's higher than the dielectric value, and then you would produce an irreversible process. Okay, so when that happens, Okay, you are producing pore. So when that happens, you would have a lot of holes onto your cell wall, okay, onto even the microorganism cell wall. So what happens is that when those pores, it's a lot on the cell wall, all the water will be pushed inside your cell wall. Okay, so let's say if you are treating your fruit juice with the pulp inside and everything, so the pulp will become your cell wall, and sometimes the pulp will be bigger. It will become lumpier because of the pore that was formed and all the water goes inside it. All right. Okay, so then swelling will happen, and then eventually cell lysis will happen, inactivate cell. This will happen to your microorganism, right? But then this process will only happen depending on the intensity of the electrical field and the number of pulses, and of course the duration of pulses. So this is what happens, right? So this is an irreversible electroporation. This one is a reversible electroporation. Okay, main processing parameters. The first one is what we call EFS, electrical field strength. So pore formation will occur when transmembrane potential exceed 1 volt, and with decreasing cell size, the required field strength sharply increases. Okay, when you have a lot of pulp in your fruit juice, okay, and at a small size, so then sometimes you may need higher EFS, right? And variation of cell shape can also cause considerable increase of your EFS. Okay, treatment time, specific energy impulse geometry. Okay, I'd like to show you this. Okay, there's two types of pulse electric field. One is what we call an exponentially decaying. This one is a square wave pulses. This one is much more better in order to treat your food product. The voltages are in the range of about 10 to 60 kilovolt. Both are effective for microbial inactivation, but the square wave pulses save energy and require less cooling effort. And because why? The holding time, or what we call the duration period. Okay, this one is the duration period. It is being measured in terms of microseconds. Okay, so this one is much longer in comparison to this one. Okay, this one, it does not hold to the maximum period at the time. For quite some time, it exponentially decay at a maximum rate. Okay, so basically you need to have these two. Okay, so EFS, pulse duration. Okay, the higher it is, the more that you get in irreversible electroporation. So another thing that you need to know is, of course, the conductivity, electrical conductivity. Media rich in ionic species such as tomato juice present problems achieving a significant voltage, since smaller peak field strength is generated across the treatment chamber. Okay, because tomato juice has a lot of ions inside it, so it clashes with the electrical ions that is being produced by the pulse electric field. So the membrane becomes weakened and more susceptible to an electric pulse in media with higher ionic strength and causing higher permeability and structural changes. Okay, another thing that is very important for you to note is that when you are using pulse electric field, you need to make sure there's no air bubbles within your treatment chamber, because when that happens, the air bubbles cannot withstand high electric field strength. So then what happens is that there will be a significant drop to your field strength that can cause food safety issues later on, because the microbial inactivation efficiency has become lower. Right? So any foam forming product like beer cannot be treated with pulse electric field, right? Okay, again, sometimes mild heating may need to be used in combination with pulse electric field, because it increased the efficiency of it. All right, and again, going back to the cell characteristics. Okay, in general, gram-positive organism seems to be less sensitive. Okay, higher efficacy can be achieved for cell in logarithm growth phase, and at times it's not possible to sterilize food. Okay, another thing that you need to consider also is the design of it. Okay, sometimes you may consider a square design like this. So your all electrodes will be on all 4 sides of your vessel, and then your food product will go inside. So basically all direction. The electric field can come from all direction. Or you could also use a circular shape like this with the inside. You can have another bigger electrodes in the middle of it. And you can also have an hollow circular type. Okay, so the electrical field will look something like this. If we were to compare pulse electric field with the high temperature short time, okay, so the pulse electric field treated and control sample at initial antioxidant content is almost the same. Okay, so if you look at it, the pulse electric field and the control is almost the same, but for the heat, it degrades quite high. Sorry, I'm not talking about antioxidant, it's ascorbic acid. Okay, so the degradation of vitamin C is quite high when you are using with heat. Okay, and again, when you look at the lightness of it also, okay, when heat is being used, the lightness of your fruit juice is orange juice is quite detrimental. Okay, because we do not want orange juice that doesn't have the orange color. We want orange juice to be orange. Okay, so these are some of the commercialized pulse electric field. These are being used for the liquid. These are being used with the tomatoes and the potatoes in the Netherlands. Okay, why we use pulse electric field for potatoes? Because it can produce French fries that are flexible and bendable. Okay, we do not want any French fries to be broken by the time it reaches to the consumer. So this is a very good French fries. Okay, so unexplored potential of pulse electric field, there's a lot more of research that needs to be done, especially on the unknown destruction kinetics of microbial pathogens, especially on the botulinum. Okay, identification of proper indicator organism, uniform delivered treatment, impact processing condition, and of course, with additions of food additive, can it replace the mild heat treatment? Those are the things that we need to research on. Right, we move on to power ultrasound. When we are talking about ultrasound, there are two categories of ultrasound. There's one what we call the low intensity ultrasound, another one what we call the high intensity ultrasound. Okay, high intensity is also known as high power ultrasound. Okay, and low intensity is also known as low power ultrasound. So low power ultrasound are the one that is being used when you want to look into the physical-chemical properties of your food product. Or maybe you want to scan the belly of a pregnant mother. So you would use a low power ultrasound. But for higher power ultrasound, it's basically used to alter or to modify either physically or chemically the properties of your food. So basically you can generate emulsion, you can disrupt any cells, kill off any microorganism, promote chemical reaction, inhibit any enzymes, standardize meat, okay? And of course you can modify the crystallization process of your ice cream making, let's say. The principle of ultrasound, there's 5 of them, okay? Basically we look at the sound waves. Ultrasound waves are similar to sound wave, but their frequency are far too high for perception by the human ear. So these are human ears. It's about 20 to 20 kilohertz. And power ultrasound has a lower frequency. Okay, so lower frequency is around here, and the higher frequency is for diagnostic, for the sensor, for you to check your belly for babies and everything. Okay, so this one is used as a diagnostic. So ultrasound has the properties of sound wave. It can reflect, it can interfere, it can absorb, it can scatter, and it can be propagated through solid, liquid, or even gases. Okay, so the wave characteristics are 2. One is what we call the longitudinal wave, and another one is what we call the shear wave or transverse wave. Okay, the usage of it really depends. Okay, the direction of wave for the shear wave is basically left and right. But for the longitudinal, basically the wave is up and down, and the particle motion is also up and down. Okay, if you look at this, if you were to look at for instance, you're talking about orange juice. So orange juice basically use a longitudinal, so where the particle motion goes up and down at liquid at about 20 degrees C is about 1,540 velocity or meter per seconds. But at a frozen, the velocity is about 3,300 meter per second. So that is the velocity of your particle motion. Okay. Another thing that you need to consider when you are using ultrasonic is about the stable and transient cavitation. So you have a compression and of course the rarefaction. So what happens is try to follow these bubbles here. Okay. So you would have, when you are at a compression stage, your bubble would be smaller. When you are at a rarefaction stage, your bubble would become bigger. So when this process keep going on and on and on, at a point, it can burst or explode. When this happens to explode, this is what we call a transient cavitation. But when your bubbles maintains its size, okay, this is what we call a stable cavitation. And often it just produces bubbles during your extraction or during your treatment. Okay, what happened when your bubble bursts? Okay, because of that burst of bubbles, it can produce what we call microstreaming, and another one is what we call a microjet formation. So what happens with microstreaming is that it produces a shear that can affect the textural properties of your food product. So imagine this is your food product, the cell wall of it. So when you have a microstreaming that is moving very rapid and very aggressive, then it produces a shear and then it changes the texture properties of your food product. Okay. When you have a microjet, what happens is that when that bubble bursts, it produces a jet propulsion of liquid from that bubble itself. So that jet propulsion will produces a very high velocity of liquid coming in your food product, and then it can rupture the wall of your cell, of your plant cell or your microorganism cell. Okay, so the jet formation sometimes comes with also what we call localized temperature at about 1,000 Kelvin. Okay, but because it is a localized pressure and often it does not go to your liquid, to all your liquid. It only happens to that particular point only. So your liquid would not increase in terms of temperature. Okay. So the bubble oscillation, okay, we're talking about the stable cavitation. So what happens is that that bubble itself can push or even pull. So then it will produces again textural changes or maybe it's not electro, it's a pore formation. It can produces what we call holes into your cell wall, right? Okay, so if you look at this, when you have a very low frequency, okay, high power, it produces a bubble diameter that is bigger. So because it reduces the frequency, it carry more energy. But when you are dealing with high frequency, low power that is used for diagnosis and everything, it carry less energy, so the bubbles is much more smaller. Okay, so ultrasonic mechanism, again, I've mentioned about the jet formation. This is when what happened when your stable cavitation, stable bubble become transient cavitation. So it causes a microjet formation. And at times, the transient bubble can collapse. It emits light and causes a sonochemical reaction. And sometimes you can see a very what we call a beautiful light coming in from your ultrasonicated product, but not necessarily in your food. I have never seen orange juice turn into sonoluminescence. I have not seen it, but maybe in chemical. Okay, so coalescence inhibition, when solid particles present between the bubble, it inhibits the larger bubble formation. So when you have solid particle that present between the bubbles, so your bubble would not become bigger. Right, so components of ultrasound, there's two. Okay, there's one what we call probe. So this is what probe looks like. Okay, so the one that we have in UPM, I often use with probes, but there's also what we call the direct ultrasound. Direct ultrasound looks something like this. It has a water bath type. Okay, so often we have our electrodes or ultrasound transducer. The one in UPM, we have it at the side of the vessel. This one coming in from the bottom of the vessel. So using the ultrasonicated water bath, you can use either directly, you put your food sample inside, or you can use it inside the jar. So this is an indirect method. Okay, so these are some of the comparison. In terms of effectiveness, I would say probe sonicator is much more effective, but the limitations of the probe is that it depends on the size of your probe. So your probe, if it's very thin and then your jar is quite big, and then the frequency or the sound wave cannot go throughout your vessel. Sometimes it's very limited to the side of your probes only. But for the water bath type, at times it only happens at the bottom. It does not go through directly to your food product. So that's the issue. Okay. So the critical parameters, these are listed by the US FDA, basically on the amplitude of the ultrasonic wave. We need to make sure the exposure or the contact time, the type of microorganism that you're dealing with, volume of food to be processed. Okay, so this is very important, the volume of food. So the larger volume that you have, it's much more difficult to treat it with ultrasonic. Okay, and the composition of food, and of course the temperature treatment. What I would like to focus on is on the application of ultrasound. Ultrasonic is a very diverse technology that you can play with. Okay, because why? The applications are very diverse. You can use it for antimicrobial effects. Of course, you can kill off any microorganism, but it also has a heat transfer and mass transfer effects of it, where there's also textural changes when you are using ultrasound, where you can also produce or homogenize milk. Okay, you can also use for fermentation, crystallization. I don't want to cutting is I'm not going to focus on the cutting part, but it can also do degassing or defoaming of your food product, cell disruption, enzyme activity and such. Okay, when you look at the microorganism inactivation, of course, by in peptone water using a 10-minute treatment, 4 log easily kill off salmonella. But in chocolate milk, because of the soluble solid inside of it, you need a minimum of 30 minutes of ultrasonic treatment. And it only produces about 0.8 log. Okay, so that's not a lot. So meaning to say that chocolate milk, the soluble solid inside the chocolate milk itself, offered a significant protection against the microbial inactivation. And then if you look at this research, is done basically using a sonicated poultry in a chill bath using chlorinated water. So just by using sonication only, there's a reduction of about 1 to 1.5 log reduction. But using a chlorination water only, less than 1 log reduction. But the combination of sonication and chlorinated water, there's about 2.5 to 4 log reduction in cleaning of the chicken. Okay. But having said that, sometimes using a mild frequency, okay, of ultrasound, you can assist fermentation process. Okay, this is what they have done on Lactobacillus brevis. Okay, so yeast extract. So they use an ultrasonic assisted fermentation. If you look at the frequency that is being used, is about 23 kilohertz. And the amplitudes is about 10 to 15 micrometer for about 3 to 5 minutes. And these are the various temperature that has been used. Okay, so basically it can, at a point, 32% increase of GABA yield, 36% increase in protein hydrolysis, higher cell count, higher cell membrane permeability, intensified acidifying rate. So it can help with the fermentation. But only the but is you cannot use beyond 10 micrometer amplitudes, because beyond that, it kill off all the yeast inside this liquid medium. All right. Another usage of it is homogenization. Basically, you can produce a very good oil in water and also water in oil, right? But the opposite end of it, So besides just to homogenize, but it can also be used to defoam, meaning making sure that your product does not have any bubble. Okay, like in a beer company, okay, they do not want any bubble inside your vessel, because the thing is the bubbles will fill in most of the headspace, and sometimes it can flow out of the vessel, so they do not want any bubbles inside their vessel. So they would use the ultrasonic transducer, so basically it will move around to make sure all these bubbles can dissipate. And there's also using ultrasonic in a can filling machine. Okay, so defoaming is very, very good. Another method of ultrasonic is drying. Okay, why? Because high intensity ultrasonic wave can cause a rapid series of alternative compression and expansion in a similar way to a sponge when it is being squeezed and released repeatedly. So this is what we call a sponge effect. Sponge effect can look something like this. Okay, so basically the water is being squeezed out, goes in, squeeze out again. So this force involved by the mechanical mechanism can be higher than the surface tension, which maintains the moisture inside the capillaries of the material. So in addition, ultrasound produces cavitation, which may be beneficial for the removal of moisture strongly attached. Okay. Another way of using ultrasound as a drying method is basically using a vibrating structure. So basically, it produces a good impedance matching where you have the sponge effect and, of course, better drying effects. So this is a very good combination of the cavitation and the sponge effect, so you can reduce the initial moisture content. Okay, these are some of the equipment that was being produced. Okay, this one is to dry carrot slice. The frequency is about 20 kilohertz, static pressure, but it comes with an airflow and air temperature of about 22 degrees C. This one uses for carrot, apple, and mushroom slices. Again, same frequency. Okay, airflow is about the same with this one, but the temperature is about 20 to 55 degrees C. So if you look at it, it's a bit different. Okay, this one has a vibrating plate. The ultrasonic transducer is attached to the vibrating plate. So the sample is in between. Okay, and you have the hot air flowing. And then you have the suction system to suck out all the moisture and everything else. And this one uses the sample here. So it's a rotating plate. Okay, so it moves about and the plate will vibrate it. Okay, the best part is the improvement of the drying rate is about 70%, and you would have a lower final moisture. Okay, and this one reduction of drying times for carrot up to 3 times. Apples is about 50 to 77%. Mushroom is about up to 83%. And reduction of drying times for carrots is about 60%, which is quite good. And apples is about 233%, and mushroom is about 75%. I guess because mushroom has fibers that attach the unbound water, the bounded water inside it. Okay, so by using this frequency, as you increase it, also the drying time would be much the sample weight would decrease much faster. Okay, so these are some of the industrial application. You would have this one is a smaller scale, this one is the benchtop, and this one the industrial scale that looks something like this. Okay, it's very, very big. Disadvantages of ultrasound, the issue is it again, trial and error for every type of food available. Okay, so the lack of standardization, so making operating frequencies and power level makes comparison between different effects were difficult. Okay, and the direct contact between probe and food medium, because we do not want any cross contamination, so this is an issue. Okay, the effect of color and antioxidant has been reported in some sonicated samples due to degradation of pigments at high energy levels. And during emulsification and process of vegetable oil, metallic or rancid odor has been detected only for insoluted oil and food. Okay, so I guess this is it. So I come to the end of my lecture for today. I'm sorry, Ibu, I've taken about 20 minutes of your time.
It's okay, Dr. Nadiah, and
All right.
because the agenda a little bit late, so I'm
I
still here.
see. Okay. All right.
The committee has not called me yet, so
Okay.
it's okay.
So it's
Uh,
good news for me then.
yeah. Okay. Next we continue to discussion, question and answer. If there are any question, please ask directly to Dr. Nadiah Karim. Oh yeah, we have Naufal Ramadan. Raise hand. Okay, go on.
Okay.
Naufal, can you
Okay,
open
hello.
your camera maybe
Camera
so we
right.
can?
Okay.
Okay.
Okay, so I have some questions about like the high pressure processing and the pulse
Ah,
electric fields. Yeah.
okay.
Maybe I will tell you about the HPP first. Like, um, while high pressure processing can extend like shelf life,
Mm-hmm.
some consumers may perceive like HPP treated products as overly processed or unnatural. So like in Indonesia, how could Indonesian food manufacturers leverage HPP while addressing potential customers' perceptions, particularly in the context of the growing demand for clean label and minimally processed products?
Okay. HPP usually we don't add any preservative. That is the good part of HPP. So in that sense, I think there's a lot of awareness that you need to do. One of the company in United States that was the first pioneer of using HPP when he wants to tackle the consumer, to tell them this is a very good technology. We do not use any added chemicals or preservative, but how does it kill off the microorganism and extend the shelf life? They actually produce an infographic at the side of the box. So they show the mechanism of how they kill the technology by using a cartoon. Is easier to be understandable, it's easier to be understood by the consumer. So that is one of the ways. I guess not even in Indonesia, I think in Malaysia also, we would like to increase the awareness of HPP. Even now, people not a lot of people know about it. So that is one of the ways that I feel that is very approachable. We can do maybe social media awareness, telling people, how. Remember when back then we do not know how COVID, transmitted and everything. So I think the same way we can do that, by using social media, radio platforms, TV platforms, we can inculcate or educate our consumer, even the kids at school. So yeah, that is one of the ways.
Okay, thank you. And next, I have a question about the PF.
Okay.
Uh, you mentioned that the presence of air bubbles can cause significant drop in the electric field strength,
Yes.
compromising the effectiveness of PF treatment in the context of certain foamy or aerated agricultural products in Indonesia, like Indonesian fermented products of foods.
Mm-hmm.
So what strategies could be employed to mitigate this issue and ensure adequate electric field exposure for microbial, inact inactivation or other desired outcomes?
Okay. There are two methods. One of the method is for you to defoam your product first. Maybe you can use ultrasonic to decrease all the foaming bubbles inside your product. Another method is to pump your product from the bottom to up, going up. It's not from up to bottom, because the flowing of your liquid sometimes when it is very high velocity, it can produce bubbles within your food product. So pumping your liquid from the bottom, from the bottom. Let me draw. So let's say if you have your liquid vessel here, your liquid product, so you can pump your product from here, going directly to your pulse electric field. Okay, so
Uh-huh.
this one basically can avoid any air bubbles. So you do not have any bubbles forming within your food product. So the liquid flow looks like that. I hope you understand.
Yeah, I understand.
Okay.
Especially like the defoaming the
Yes.
so it's like f fusing two methods, like you said, like using PF first, and if it's really foamy, you can defoam it with the ultrasonic, right? Yeah.
Yes.
Yeah,
Yes.
I understand. Thank you for
Okay.
the answer for a
No
couple of my
problem.
questions. Yeah,
No
thank you.
problem. Thank you.
Thank you, Noval, for such two questions. Is there any from student? Okay. We will wait for your question. Maybe I will ask Dr. Nadiah. Behind me, there is a key sonica sonicator.
Oh, I
So
cannot
actually,
see,
oh yeah, maybe.
but that's
Yeah. Okay. So we
okay.
already have this equipment for almost 3 years, if I'm not mistaken. Uh,
Okay.
so
So you are using that for the bunga telang extraction.
yeah,
I
for practical
see.
skill for student and also for research. And
Okay.
one problem that I faced dealing with my equipment, we cannot
Uh-huh.
set the frequency. Set the frequency.
Yes. Yes.
Yeah. So we
Yes.
have only one probe and one frequency. So
Yes.
I just uh, vary the amplitude and also the length times processing. So
Yes.
I want to know what will happen if we adjust the frequency inside the ultrasound. Maybe you have any experience
Okay.
in ultrasound batch
Um,
or probe type. Okay.
okay. Actually, the types of the probe is the one that emits the frequency. So basically, if you like a different frequency, you need to change the probe type. So bigger probe will give you a bigger frequency, because the thing is that because it is attached to an electrical source, right? So this thing, the probe here, is actually made out of I forgot what it is made out of. And often this thing are the one that is producing the sound wave. Okay, so depending on the type of the probe that you have, okay, how big is it and everything, so only then you can change the frequency of it. So unfortunately, yes, I have to admit on that part that for whatever the probe that you have or you buy, it has a fixed frequency. The only thing that you can change is the amplitude and sometimes the power of it. Yes, so I remember when I was doing my PhD work, I have to buy my own probe because the specific frequency that I would like to inactivate the enzyme inside the fruit juice that I was dealing with at that time, it was not available in the lab, so I need to buy my own probe to kill it. So yeah, so for the type of frequency that you like, you need to buy a new probe. So the bigger the probe, the bigger the frequency.
But for food application, it is better using the smaller probe or using
Uh,
the bigger.
Depends.
Oh,
Depends. Depends if your food is high viscosity, like you're talking about maybe mayonnaise type of food, you would need a bigger probe because the sound wave, because it's sound, right? So it needs time to go through from one end to the other end. So if your food product is very thick, sometimes it may not be enough. So you will need a bigger probe that can cover a larger surface area. So then it will go from one end to another end. So, but for a low viscosity food product like fruit juice, then maybe you can use a thin probe, no problem.
If I'm not mistaken, we have only 2.5 inch probes.
2.5 inch.
0.5 inch, I think.
Okay.
And it works like pulse wave. So
Okay.
we have to shut down, not shut down. We have to give time sometimes, and then we
Okay.
can start again. So
Yes.
we cannot operate from 1 up
Um,
to 30 minutes in the in the
true.
batch. Yeah,
Yes.
yeah. So
I think we basically have the same problem because
yes.
mine is also like that.
I think the same ultrasound sonicator. Sonicator.
Yes.
Same with this
But yeah,
slide
I cannot see.
in my yeah.
Okay. The one thing with changing the probe, when you have a bigger probe, it would emit high frequency, so you will have high energy. When you have high energy, it gets hot very fast. So
Yeah.
it's good that you would do maybe ice bath outside. So I usually put ice out here.
Mm.
So just to control the temperature so that the temperature would not go higher than usual.
Yeah, same with my experience. So when
Okay.
we extract white tea using ultrasound, it rise about 40 degrees centigrade. So
Okay.
maybe average 30 degrees centigrade for the
I
increase of the
see.
temperature. So
Okay. May I ask on the
it's better
results
to put
of
ice on
oh,
the result for
sorry.
white tea.
Sorry, Ibu.
Yeah.
I thought you are finished already. May I ask the result for your bunga telang extraction in comparison to the microwave ones?
Okay.
Is there any difference?
Student, can you explain to Dr. Nadiah because the result is in yours? I haven't seen yet.
I haven't seen
Oh,
it yet.
yeah. Yeah. Maybe one of you can tell the result, extract bunga telang with microwave assisted extraction compared to ultrasound assisted extraction. Which one better, or which one produced high yield? Anyone? Vicky, or maybe Raihan, Fadil? Volunteer? Any volunteer? Priscilla, maybe? Or you have to see your note before? Which one better?
Yes, which one better? Or is there any color changes in comparison to the two methods?
Yeah. Picky, maybe? Last time you tell us about microwave assisted. Have you done with ultrasound? Picky?
Iya, Bu.
Bisa dijelaskan ke saya dan Bu Nadiah hasil perbandingan dari ultrasound assisted sama yang microwave assisted untuk bunga telang?
Untuk hasil dari segi perubahannya, Bu, atau bagaimana?
Dari warna, mungkin warna atau dari
yes.
yield-nya, rendement yield.
Tapi saya menjelaskannya dengan bahasa Indonesia tidak apa-apa.
Iya, nggak apa-apa.
Boleh. No problem.
Untuk praktikum di pertemuan sebelumnya itu kami itu sudah melakukan mengenai metode itu ultrasound dengan yang microwave.
Okay.
Untuk dari sendiri untuk microwave itu kami menggunakan perlakuan berbeda terhadap dayanya. Untuk dayanya sendiri untuk microwave itu ada 30%, 50%, dan 70%. Untuk perubahan sendiri dari microwave itu dari hasil bunga telang, ekstraksi bunga telangnya itu larutannya itu berubah warna. Untuk 30% itu masih biru agak biru. Namun untuk hasil daya yang lebih tingginya itu menunjukkan warnanya itu menjadi lebih keunguan. Dan dengan metode ultrasound pun sendiri pun dengan ultrasound pun menggunakan amplitudo yang berbeda. Kami itu menggunakan amplitudonya sekitar menggunakan 3 perlakuan amplitudo, yaitu 50, 70, dan serta 100 amplitudo. Di mana apabila amplitudonya itu meningkat, hasilnya itu hasil larutan bunga telangnya itu memiliki tidak memiliki, namun untuk warnanya itu tidak memiliki perbedaan untuk ultrasound, namun aromanya yang lebih kuat untuk menggunakan metode ultrasound. Berbeda dengan berbeda untuk mikro itu perubahan warnanya saja terjadi, namun aromanya tidak sekuat dengan
Dr. Nadiah, excuse me and all class. Saya mohon izin dulu dipanggil oleh Nadiah. So
boleh. Okay, see you next week, Ibu.
Making class. Okay, Dr. Farah, Teh Farah will accompany you.
Okay, no problem.
Emerging class. Thank you so much.
No problem. Take care. Have a nice weekend. Sorry. Yeah, thank you, Vicky. Okay, so that's very interesting in the sense that the aroma is quite okay, maybe because of the cell wall rupture that caused the aroma to increase in comparison to microwave assisted extraction, right? Yeah. For microwave, aromanya macam mana?
Untuk aromanya itu tidak sekuat dengan menggunakan metode yang ultrasound.
I see. Kalau saya boleh tanya, aromanya macam mana itu? Like baunya bau apa? Bau pokok, bau daun?
Buat aroma dari bubuk telangnya.
Okay. Okay, that's interesting. So, but if the color is not changeable and is comparable to the MAE, do you think yang mana lebih bagus untuk digunakan? Ultrasound atau microwave assisted?
Menurut saya apabila ingin memperkuat aromanya itu lebih baik menggunakan ultrasound, dan apabila karena dari hasil larutannya sendiri pun menggunakan microwave. Namun dengan microwave itu kita menggunakan metode panasnya itu lebih merata juga, sehingga warna dari panas itu ada sedikit perubahan itu. Berbeda dengan ultrasound sendiri. Dengan ultrasound itu karena adanya menggunakan frekuensi getaran, sehingga mungkin tersebut aromanya itu semakin kuat karena adanya peristiwa kavitasi.
Yes, could be. Okay. What would make your experiment interesting if you were to compare the energy consumption for these two? Okay, consumption of using the microwave and using the ultrasonic assisted extraction. Maybe you could calculate that. Maybe just a recommendation, but then you can discuss with Dr. Asri later on. Hi, Dr. Farah. You're on mute. Okay.
Assalamualaikum.
Waalaikumsalam. Good to meet you.
Okay, nice to meet you too, Dr. Nadiah. I'm sorry to have to take over.
No, it's okay. It's okay. I understand. Yeah, that's what we do at times when we are being called, so we just go.
We just divide the task one for another.
Yes, understand. Okay, we are just discussing now on the ultrasound and of course on the HPP and the pulse electric field usage in our experiment. So one of Dr. Asri's student, Vicky, just now mentioned the extraction of bunga telang. So yeah, he is using microwave assisted extraction, and to compare them with the ultrasound assisted extraction. So he has mentioned the aroma of the bunga telang for the ultrasound is a bit high in comparison to the microwave, but for the color, microwave seems to give out color better in comparison to ultrasound. So yeah, I'm still considering what happens actually during the ultrasound that makes the color change. So yeah, it's an interesting thing to learn actually, but because At the moment, I haven't tried any extraction for the color using ultrasound. The only experiment I've done using ultrasound is actually to inactivate enzyme and to extract pectin. Pectin for jam, yes. This one from, do you know limau Bali? Kita sini di Malaysia we call it limau Bali. Or sana they call it maybe pomelo. From yes, from limau Bali peel. So we
Jeruk
extract the
Bali,
pectin.
maybe.
Jeruk Bali,
Yeah.
betul. That's true. Okay, so I use the peel of the jeruk Bali to extract pectin to use in making jams. So that's what I did. Okay, any other questions or maybe discussion from the students?
Oke, silahkan teman-teman sekalian untuk bertanya. In bahasa is okay, right?
Boleh, no problem.
Silahkan teman-teman. But for
Okay.
your product is powder or in what form? Dr. Nadiah?
Pectin. The
Mhm.
pectin. Oh, okay. After extraction, yes, I dried them into powder form. So then because it extended the shelf life, right? So that's why. I forgot to mention that with ultrasound, at times we need to be careful because the usage of ultrasound at times can produce electrolysis. So electrolysis is basically the corrosion of your ultrasonic probe, and it can contaminate your food product in three ways. One is in the physical way, in the sense that sometimes we can, when we analyze your food product, there's traces of heavy metals inside your food product. Another way is changing the chemical reaction of your food product. So at times that's why using ultrasound to produce homogenization in oil and water. For instance, mayonnaise sometimes can produce rancid flavor. You have a metallic taste of your product. So yeah, I have to remind you guys that on the ultrasonic, and another thing is on the pulse electric field, because the pulse electric field uses an electrodes, and because of the high voltage, it can corrode your electrodes. So then another thing is that because of the electrodes is in direct contact with your food product, so often we would recommend to you when you are doing experiment, it's better that you analyze on the heavy metal traces in your food product, because of course you want your food to be safe, right? So not just from the microorganism, but of course on the traces of heavy metals. Kita tak nak those any toxic compounds in your food product. Okay. So any type of metals that is in direct contact to your food, and when it produces any type of energy, you need to check on the traces of heavy metals. Okay.
There is a possibility contaminant from
Yes.
metal.
Yes, betul. I have done a research on goat milk using a pulse electric field, and because the goat milk has to go through the treatment chamber and in contact with the electrodes that is being used in the pulse electric field, so we had to check on the traces of heavy metals, and it was good to know that no corrosion happened during that treatment. But then again, I have to be careful too, because when I was using that pulse electric field, it was the equipment was quite new. But after sometimes, I think after, a certain cycle, maybe after 500 hours or, 1000 hours of using pulse electric field, maybe electrolysis would happen. Then perhaps we need to study on the lifetime of that electrodes itself. So I guess it's the same for the ultrasonic probe. It's not that, even though the probes may look like it is intact, it's not damaged, it's not broken, but at times because of the traces, the corrosion that happens is very, very minimal. We cannot see. But if you look closely, sometimes there's going to be pore formation on the probe itself. Sometimes when we look at the under microscope, there's going to be very, very small pore onto your probe. So these are what we call the traces of heavy metals. So it could be, depending on the type of probe that you use, if it's iron, then you need to check for iron on the traces. Okay.
Maybe from students, is there any question? Is there any recommendation treatment to reduce or to make impact of metal is low, Dr. Nadiah?
If it's in industrial setting, it's quite tough because usually we have a metal detector, but metal detector is for a big metals, right? So for small metal traces, usually are not visible to the eye, so it's quite hard for the metal or the magnet detector to pick up on the metal traces. But maybe perhaps you could do a detailed analysis, maybe 6 months after using your pulse electric field, and you use maybe just random tests just to check on the traces of the metals. I think that is the best way, because sometimes we cannot avoid using this technology. There's going to be the disadvantages of it, but at the same time, because of the advantages outweigh the disadvantages, we use that technology. That's why I mentioned to Mr. Fiki just now, it's good that we were to have an energy consumption calculation so that we can justify the advantages of using certain certain non-thermal technology over the other. Yes. Any other question?
Maybe we have to mention participant.
We have to mention names. Okay.
Okay.
Mr. Noval already, but no, okay. We have several others. Aina. Anyone have any questions?
Maybe Nurul have any question?
No questions.
If no any question, maybe Dr. Nadiah will give you question.
Okay. Soalan apa ya? Okay. Next week they are going to have presentation. So I guess Dr. Asri has discussed with them. But there's going to be 4 groups, yeah, if I'm not mistaken. So 2 of the groups maybe can present something on radio frequency and either infrared heating or maybe ohmic heating. So you choose any of those treatment. And please also choose different food industry, yeah, because I think last last year we have seen almost the same industry for each of the group. Everyone wants to treat juice product. So please, maybe my recommendation is that perhaps this is the best time that you research on your very unique Indonesian cuisine that you would like for me to know and for me to also understand and learn how the processing techniques, how to cook the product, how you can expand the shelf life. So I think that will be good because again, this is going to be an opportunity for me to learn about your culture too. And then for the other two groups, and maybe you can choose either using HPP, high pressure processing, or pulse electric field, or maybe you can use ultrasound that can be incorporated into your food processing also. Again, choose different food industry and highlight your Indonesian culture. I would love to learn about that. Okay. Because I think we have, you guys, especially Indonesia, has a very diverse food products, called cottage industry, or what do you call traditional food products. So I would really love to learn about that. Okay.
Interesting
So
idea, Dr. Nadiah.
yes, I think it's the first time I thought about it. So yeah, because I think oftentimes Malaysian and Indonesian food are not much different, but sometimes the certain elements that differentiate them. Maybe the processing part, maybe the ingredient part. So yeah, it's a good time for me to also learn about it. Here in Malaysia, I think the most popular Indonesian cuisine are basically ayam penyet. I think coming in from Indonesia, right? Now they have geprek, ada
Yeah.
ada gepuk, I think. So there's a
Yeah.
lot. Yes. So I learned a lot about food, Indonesian food, especially sate Minang or sate Padang.
Yeah, sate Padang,
Yeah,
right.
sate Padang, yes. It is quite different than sate in Malaysia.
Oh,
Yeah, I think kalau di sini satenya dimakan dengan kuah kacang. Tapi sate Padang is not kuah kacang kan? It's not.
right.
It's a bit different. So
Yeah.
yes.
And spicy. The sauce is
Yes.
spicy, right? Sate
Yes. So it's a bit different. But I love it nonetheless. And one thing I've noticed that Indonesian likes our pineapple tart. Or they call it nastar.
Yes.
Yes. Yes.
Okay. Maybe it's like Chinese traditional food, if I'm not
Yes.
mistaken. Yeah.
Okay. Here in Malaysia, I can't remember what's the origin of nastar actually, but we often have it during Aidilfitri. So sometimes it becomes a Malay food, sometimes it become a Chinese food. What I notice is the size of it. Nastar for Chinese New Year usually much bigger than nastar for Aidilfitri. So that's the difference. Other than
Yes.
that, it tastes the same.
Aidilfitri is bite size maybe. Yeah.
Yes,
Than
true,
Chinese.
true. Than the Chinese. And usually Chinese tends to go into the traditional part of it, meaning the nastar is the original form and original ingredient. But for the Malay, sometimes we add cheese on top of the nastar. So it's a bit different. I don't know, maybe because the saltiness complements the sweetness of that nastar. So I don't know. I haven't tried it, so yes. What else? So it's interesting. Indonesian has dodol, right?
Yeah. Right.
Do you call it dodol or something
Dodol.
else?
In West Java, it's called dodol.
Okay.
Or in Central Java or East Java, sometimes it's called jenang.
Jenna. Okay, that's
Right.
interesting.
But the ingredient maybe it's not different.
Oh,
Just
it's not different.
nah, form and taste is
Still the same.
similar. Yeah, yeah, same. But
Okay.
we call it in West Java we call dodol. In
Dodol.
Central until East Java we call jenang.
Okay,
Yeah.
okay, that's interesting.
Yeah.
Okay, sini di Malaysianya masih dipanggil dodol, tapi there's a different form of dodol. Sometimes they produce a dodol that is very loose, very liquidy. So they call it kelemai. So
Calamine.
kelemai, yes. So
Yeah.
it's very runny. Then you have to eat it with a spoon.
Okay.
So the dodol is actually when it's in solid form, and you have to cut it with a knife. So that's what they call dodol. Okay.
Okay.
So
Maybe
yeah, that
calamine, I think, similar like in our Eastern food, it's called
ah,
papeda.
okay.
The ingredient is sagu.
Oh, using sagu.
Yes. But
Okay.
it's still like
Still
what we
tastes a bit
say,
like dodol.
runny like calamine.
Okay,
Okay.
I see.
Yeah, papeda.
Okay.
Oh, yeah.
What is the container? They put it inside dalam apa ya, Ibu? Yang untuk yang runny dodol tadi?
Uh,
Kalau di sini digunakan daun mengkuang.
Oke.
Ah,
Kalau dodol kita hanya menggunakan plastik saja.
I see.
Ya,
I see. Tapi it's solid lah, like kena
solid.
potong.
Ya,
Okay.
betul. Tapi in West Java, we call Cililin area.
Cililin.
Yeah, there is like dodol, but we call wajib.
Oh,
Wajib.
wajib.
Yeah.
Okay, okay.
Okay, and it is packaging using, I don't know what the leaf, but it's packaging with the leaf.
With leaves.
Yeah.
Okay. Sini wajib is something macam dodol ingredientnya, but guna beras pulut, glutinous rice.
Oh,
Ah,
okay.
yes. So
In,
itu what we call wajib.
I think it's not different because the ingredient from beras ketan.
Okay.
Yeah.
It's the
And
same.
yes, and we mix with coconut and
Yes.
gula.
Sugar.
Yes, brown sugar. Yeah.
Yes. And then we cook it until it's very sticky.
Yes, right. Similar.
True. Okay, Ibu, I think we have come to the end of our lecture for today. Maybe you would like to take a picture with the
Okay.
students,
Baik.
right?
Oke, silahkan on cam dulu teman-teman semuanya. Oke, yang lain silahkan. Untuk tugas sudah jelas ya. Tadi sudah cukup jelas oleh Dr. Nadiah. Kalian kita memperkenalkan makanan Indonesia.
Makanan Indonesia,
Yes.
yes. I would love to know. My Indonesian experience has been limited to Jakarta and Bandung and Bali. That's it.
Okay.
So, I haven't yet been to any other parts of Indonesia.
In Sumatera maybe you have
No, not
Belum?
yet. Belum.
belum.
Belum. I would love to go. There's an invitation from University of Malang.
Oh, okay. In Java.
Yes.
Yeah.
But I haven't been. So we are still trying to discuss on the transportation at the moment.
Okay.
Hopefully I get to go. I would like to see. Indonesia is a very nice country. It's quite big.
Malang, you can go to Bromo. Bromo
Huh?
Mount. Yeah.
Oh, okay, Bromo
Gunung
Mountain.
Bromo, yes.
Okay, that's good.
And the
Okay,
food is quite good in Malang.
of course. I think everything is good in Indonesia.
Okay.
Um, my Indonesian trips usually are called food trip. So yeah.
Okay, maybe we
All
can
right.
take a screenshot first. Okay, in 3, 2, 1, smile.
Okay.
Okay.
All right. Okay, I think this is it for our lecture for today. Thank you very much, Dr. Farah. Thank you, everyone. Good to see you. So I hope to see your presentation next week. Okay? Right, take care.
Sorry,
Yeah.
Miss Nadiah.
Yes.
I just want I forgot like the first and second group are infrared and what? I'm sorry, I forgot.
Oh, okay. You can choose either infrared or
Infrared.
ohmic heating
Oh yeah.
or yes, or radio frequency heating.
Okay.
Okay?
Really.
All right.
Okay,
And then
and the others are
the
today's
others are either,
lecture,
yes,
right? The
HPP, pulse
SPP,
electric
PF, and
field.
ultrasound.
Yes.
Okay.
All right.
Thank you.
Thank you. Okay, take care, everyone.
Okay, thank you, Dr.
Permisi,
Nadia.
permisi ibunya.